The world is full of famous and beloved trios, like the Jonas Brothers, the Powerpuff Girls, Snap, Crackle, and Pop. And the Three Wise Men. Third time's the charm, good things come in threes, menage a trois. 3 is a special thing indeed. Just look at any of the Math Sorcerer's 298 books, and you'll see he constantly writes out lists of 3. And yeah, math is no exception. In math, we can use subscripts if we need long lists of things, but if we only need 3 things, there are conventional names for the 3 things depending on the context. Like, as this meme shows, the points, ABC, the unknowns, XYZ, the counters, IJK, and the sets, N, R, and C. We're going to take a look at each of these famous math trios. I'll tell you a bit about them and what makes them special, and at the end we'll discuss some of the trios that maybe should have had a spot in this top 4. And you can share in the comments what your favorite mathematical trio is. Let's begin here. In geometry, A, B, and C are typical choices for a trio of points. Using letters to name points in geometry goes way back, but in English-speaking countries specifically, of course, A, B, and C are common choices because in most English-speaking countries, people learn what's called the ABCs, which is a song, and it goes a little something like this. A 1, a 2, a 1, 2, 3, 4, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Now, what can you do with 3 arbitrary points, A, B, and C in geometry? Well, quite a lot, but certainly one important thing you can do is create a beautiful shape called a triangle. Indeed, 3 points are exactly enough to specify one triangle. Everybody loves triangles, but there's another simple shape, perhaps even more beloved by roundness enthusiasts, called a circle. And indeed, 3 points are not only enough to specify a triangle, but also a circle. Yes, there is a circle that goes through the 3 points of this triangle, and to find it, we can construct the perpendicular bisectors of the triangle's sides. For example, a perpendicular bisector to the side AB is a line that cuts AB in half and intersects it at a right angle. And to construct it, all you have to do is bust out a compass, put the fixed point on one side of the segment, and make sure that the compass is extended past the halfway point of the segment. Then draw a little arc on top and a little arc on bottom. Then put the fixed point on the other side and do the same thing, a little arc on top and on bottom. Then we'll get an intersection point on the top, an intersection point on the bottom, and we can connect those points to create the perpendicular bisector. Just like that, we have this segment which cuts AB in half and does so at a right angle. What we're really trying to do right now is find the center of the circle that goes through these 3 points. To finish doing that, we just need to construct the other 2 perpendicular bisectors. So we'll come over to this side and do the same thing. Arc on top, arc down below, switch sides, arc on top, and an arc down below. Then connect the intersection points to get the perpendicular bisector. Then we do this once more for the third side. Upper arc, switch sides, upper arc, lower arc, and then just connect the points of intersection. Now the idea is that all 3 perpendicular bisectors of the sides of the triangle will now intersect at a single point called the circumcenter. If you're careful to follow the lines closely, you can see that the 3 perpendicular bisectors intersect at this point right here. Circumcenter means that this is the center of the circle that circumscribes the triangle. In other words, it's the center of the circle that passes through the triangle's 3 points. So then we can just put our compass's fixed point on the center and make sure that its length is the distance from that center to a vertex of the triangle. And then holding that fixed point steady, we can get the circumcircle. And there we go. So you see how 3 points not only specify a triangle, but also specify a circle. There's no other triangle that has these 3 points as its vertices, and there's no other circle that passes through these 3 points. So thank God for A, B, and C, always being there to help us name our arbitrary trio of points. All right, next up, the unknowns. Oh, whoops, not those unknowns. The unknowns. Oh, wait, not those ones. Sorry, the unknowns. X, Y, and z. Typically, one will first encounter these in an algebra or pre-algebra class, and they're used to represent unknown quantities, although they're often just called variables. Really though, these are separate things, and variable is not the correct name for how people usually first encounter these. For example, in the equation 2x equals 2, is x a variable? No, x is an unknown. Variables can take on multiple values, but it's easy to see here that the only possibility for x is 1. But whether we're talking about unknowns or variables, in algebra class, x, y, and z are very popular choices. Interestingly though, if you've taken an algebra class, you might recall that tons of other letters show up too. This is my ultra-rare holographic Texas edition Larson's Algebra 1. And typically, the examples and exercises in an algebra book like this will use all sorts of variables, not just the common x, y, and z. Mathematics has its conventions, and it's not conventional that we just pick random letters to represent unknown quantities, but doing this with the variety of letters is great practice for people who are encountering this stuff for the first time. Sure, the convention is to use x, y, or z, but students need to know that any letter can serve this purpose, and when they're doing different word problems, it might make sense to use h for an unknown height, or w for an unknown weight. But yeah, x, y, and z are popular, but in these algebra books, man, it is anarchy. And it's our old friend René Descartes who first used, or at least popularized, the use of x, y, and z. In fact, he would use x, y, and z to represent unknowns, and the letters a, b, and c to represent known quantities. Now, some of you might wonder, why do we need letters to represent known quantities? If we know what a is, why would we write a? Why not just write what a is? Well, this is just for working out generalizations. For example, you might recall the slope formula, y2 minus y1, which is rise, divided by x2 minus x1, which is the run. Here, the idea is we know 2 points, x1, y1, and x2, y2, and with that known information, we can figure out something we didn't know, which is the slope of the line passing through those points. The letters are used to represent the general situation. If we know these 2 points, we can plug them into the formula and figure out something new. Now, although in algebra you'll spend a lot of time solving for x, y, and z, you'll probably spend most of your time with x and y graphing lines. Yeah, when it comes to x and y in algebra, it really is just lines, lines, lines. Oh, this sharp metal edge must be so painful, you poor thing. Blech, ugh. In the context of lines, of course, something like y equals 2x minus 4. X and y are not unknowns. Here they are variables. X can be whatever it likes, and y varies accordingly. And you know, it's unfortunate, despite how much we have to write these letters in algebra class, students don't always write them super well. Probably the most common way to write x is just as 2 intersecting straight lines, and that can get you into trouble, especially when you're maybe in an algebra class and only now trying to develop the habit of changing your multiplication symbol from an x to a dot. The worst case scenario is some people will have these straight line x's and these multiplication sign x's and these straight line y's all bouncing around the same test or homework assignment. It can become an utter disaster. My recommendation for your x, do a soft curve from top left to bottom right. Draw a straight line through that curve from top right to bottom left. Thanks to the elegance of this guy, if you're still using the straight x for multiplication, it's not the end of the world, but you should still switch to the dot. At the very least, you can distinguish between the cross for multiplication and your variable x. For y, I'd recommend ditching the straight line and make sure that it doesn't look like a G, so make sure there's some space between the tops here, and bring your tail down and around. If you don't get this extra curve on the bottom of the Y, you could risk getting it confused for a 4. Some people's 4s look a little bit like that. And of course, if you're not careful about the top situation, you could get it looking like a G or even an A. Z might even be the most difficult character here to write, but of course, you generally won't spend as much time with Z in an algebra class. But I'd recommend if your 2s look anything like a Z, then make sure you are crossing your Z's. To be extra careful, you can add a little bit of a lip to the top and the bottom, and you can always adopt the superior swan style too in order to avoid getting your 2's and z's confused. Now, you might think since the two unknowns, x and y, can be used to describe a line in two-dimensional space, perhaps if we have all three of these classics, x, y, and z, we can get a line in three-dimensional space. Here's a three-dimensional x, y, z space. In 2D space, we can describe a line by writing y as a function of x. So we might think then, if we have a line in three-dimensional space, we could describe it by writing z as a function of x and y. But it turns out it's not so easy. The equations of a line in 3D space look something like this. These are called parametric equations, and here most of the letters do represent known quantities. x1, y1, and z1 are known coordinates of a point. A, B, and C are known components of a vector, which tells us the direction of the line. However, t here is a variable. It's called the parameter, and so even with x, y, and z, it's not quite enough variables to represent a line in 3D space in the way that we typically would, which is like this. However, if instead of increasing our space from 2 dimensions to 3 dimensions, we focus on the dimension of a line, the dimension of a line is 1, and if we increase it to 2 dimensions, then we're talking about a plane. And indeed, the 3 variables x, y, and z are enough to describe a plane. Here is a plane in 3D space, and the equation that describes this plane is x plus 2 times y plus 3 times z equals 0. Now, like we said earlier, A, B, and C are great choices for points in a plane because people in English-speaking countries learn their ABCs, and this is how the ABCs start. A, B, C. However, for the unknowns, X, Y, and Z also make great choices, because in America, we actually learn what's called the CBAs. That's another song, and it goes a little something like this. A 4, a 3, a 4, 3, 2, 1. Z, Y, X, W, V, U, T, S, R, Q, P, O, N, M, L, K, J, H, G, F, E, D, C, B, A. Next up, I, J, and K. When I first saw this, I thought, oh yeah, the standard basis vectors in R3, that's a fun choice. But then I realized the meme actually says the counters I, J, and K. The OP mentioned that he had a programming background, so that explains why this was his first thought for the letters. So I, J, and K are commonly used variables to count through lists. For example, a matrix is a rectangular array of numbers, and if we wanted to multiply 2 matrices together, well, it looks a little strange if you haven't seen it before, but how it works is we take the rows of the first matrix, and each row will go through getting matched up with the columns of the matrix on the right. And at each step, like the first step here, where the row is getting matched with the first column, we multiply and add the corresponding entries. So again, we would take this first row from the first matrix, we match it up, so to speak, with the first column, multiply the corresponding entries. 1 times 0, 3 times 1, 2 times 5, and add them all up. And then the row goes to the next column, and so on. After we're all done with the first row, which would give us 3 numbers, we would move on to the second row, which would get matched up with the first column, then the second column, and then the third column. And then, of course, we would do the third row. Now, if I wanted to write a computer program to carry out this process, I could use a triple nested for loop that would begin for each row. So I'm going to take each row one by one, and then with each row, I'm going to have to go through each column. So for each row, then for each column, the columns coming from this matrix on the right, and then to do that multiplication of corresponding entries, we'd have to do for each position. And in this process, actually writing the program, you would need to use 3 counters. I might let I count through the rows, and then I could use J to count through the columns, and then to count through the positions, I could use K. So we'd start off at the outermost layer, I equals 1, so we take row 1, and then we match it up with J equals 1, that's column 1, and then we get to this innermost layer of the for loop and let the K go through the 3 positions. K equals 1 means we multiply these entries in position 1, and then multiply the entries in position 2, and then in position 3, and then add them all up. After that, the outermost loop is still on I equals 1, that is row 1, But then j can move up to j equals 2, so row 1 then moves on to the second column. In this way, using our 3 counters I, j, and k, we could do all of the arithmetic necessary for matrix multiplication. And it's likely that mathematicians are to blame for this programming convention of I, j, and k being used as the counters, since mathematicians use these letters to accomplish similar things. We often use them as what are called indexing variables, which perhaps explains the use of I for this purpose. Now, I had mentioned I thought these were the standard basis vectors at first. I'm not going to go into detail on those, but the standard basis vectors are usually written either in bold or with a hat, so I suppose I'm content to accept that these are the counters, not the standard basis vectors. As for handwriting the counters, one pro tip with the I and the j is to basically write them as backwards versions of each other so they don't get confused. So for the I like to give it a very subtle right-leaning tail, and of course dot it, and then j of course has a tail that curves to the left. Because of how these letters are used in mathematics, they're often written pretty small as subscripts to index things, so it's really important that you're careful about writing them. Since they appear so small, it can be really easy to get them mixed up if you're not careful. And at last, the sets. N, R, and C. This is the only trio in the meme that doesn't look just like normal letters. So why do these look so strange if you haven't seen them before? Well, let me tell you what these things represent. First, the big N represents a set of numbers called the natural numbers. These are also sometimes called the counting numbers, and is the set containing 1, 2, 3, and so on, and there's no disagreement about this. Now, of course, as the story goes, there was an ancient Greek who was trying to share a pizza amongst his friends and realized that the natural numbers were not sufficient to describe the world. So, to describe fractions of the pizza, and to describe the distance around the pizza as well as the pizza's area, he introduced what we call the real numbers. There's no nice way to just list the reals out like there is with the naturals, but of course, the most common model for the real numbers is the familiar number line. This is a continuous line that has 0 at the center and then goes infinitely to the right with all the positives and infinitely to the left with all of the negatives. This contains fractions like 1/8 and 2/7, and it contains irrational numbers like pi and the famous e. Now, what about the C? Well, one of the primary hobbies of 14-year-olds, at least in the United States, is figuring out where parabolas intersect the x-axis. But one of the big problems with this hobby is not every parabola does hit the x-axis. For example, the parabola y equals x squared plus 1 doesn't hit the x-axis anywhere. If we were trying to locate where it hits the x-axis, we would set y equal to 0, so we'd have x squared plus 1 equals 0, so x squared equals -1, so x is equal to plus or minus the square root of -1. But -1 doesn't have a square root. There's no real number we can multiply by itself in order to get -1. Thankfully though, very intelligent mathematicians anticipated this problem with this very beloved hobby, and so they introduced a number called I, the imaginary unit. This number is defined to be the square root of -1. So then we can get this brand new thing called a complex number, which is created by taking a real number and then adding it to some multiple of the imaginary unit. Here, A is called the real part, and B is called the imaginary part, since it's the number that's getting multiplied by the imaginary unit. Like I said, this is a complex number, and of course that's what the C stands for. Now, because a complex number has these two things, a real part A and an imaginary part B, the complex numbers don't live on a single line like the reals. Instead, they exist in a plane called the complex plane. We need a two-dimensional plane because we need one axis to represent the real part of each complex number, that's traditionally the horizontal axis, and then we need another axis to represent the imaginary part of each complex number, and that's typically the vertical axis. So real numbers exist on the real number line, like perhaps right here is the number 2, but complex numbers exist in the complex plane. Like, for example, maybe right here is the complex number 1 plus 2i. And the complex numbers don't have this problem that the real numbers have, where a non-constant polynomial can exist without a root. In the complex numbers, every non-constant polynomial has a root. And the fancy term we have for that property of the complex numbers is that they are algebraically closed. But these are all very important sets: the complex numbers, the reals, and the naturals. They're important spaces in which we carry out mathematics. And because of their importance, there is no way that simple capital letters would be sufficient to represent them. And so the cool thing is, on a typewriter, a letter could be emphasized by typing the letter, and then with a slight offset, typing the letter again, creating a double stroke. This method of representing these important sets caught on, and then when lecturers were writing them on a blackboard, they wanted to write them the same way. Thus was born the iconic blackboard bold style. It's a bold look we can give letters, but on a blackboard. Of course, the blackboard bold letters, when they're typed electronically, can look very, very nice. But if we're writing them by hand, we keep it pretty straightforward and just add an additional stroke. For example, for the natural numbers, you can just write an N and then put another stroke right there. For the reals, I like to begin with 2 vertical strokes and then do the rest of my R starting from the first stroke. For the C, you can just do a normal capital C and then draw a vertical line on the left side of it. Now, I look forward to reading your opinion about what the best mathematical trio is, and I'm sure you have some in mind that our friend Kaimax7 didn't include in this quartet. But speaking of quartets, some of you are probably thinking this is a bit of a strange inclusion, the sets N, R, and C, because unlike the other things in this meme, these sets represent very fixed and important things. They're not representing arbitrary points or unknown values or counters that run through lists of numbers. They're representing standalone, unchanging sets. Furthermore, there's another important set that isn't included here, which is of course the set of rational numbers, which is written with a Q because rational numbers can be written as quotients. These are the fractions, simply speaking. And if I was telling you all about these sets in depth, we'd start with the naturals, then discuss the rationals, then the reals, and then the complex numbers. So I mean, yeah, these are 3 famous sets, but they're really not a trio. Like, I mean, where are the rationals? Why aren't they here? They should be here, and this really isn't much of a trio. Of course, lots of people in the original thread had opinions and trios they thought should have been included, and the author said himself that it should have been the functions f, g, and h that got that last spot instead of the sets. Someone else said that the triple he forgot was the vectors u, v, and w. Yeah, those are common choices if we need 3 vectors or 3 vertices in graph theory. U, v, and w are common choices. This fella mentions that it's a real pain to distinguish between u and v when you're writing, but you really just can't be lazy if you're writing these letters. Make sure with your u you get a nice distinguished tail, and it's all the better if you can keep the left side and the right side parallel, and then with V, you really want to make sure you get that pointy bottom. But the good thing is, if you make sure you get a nice tail on your U, you can get away with a lot more roundness with your V. Just be careful, don't squish stuff together, and the W won't cause you any problems either, whether you do it straight or with curves. Someone else mentioned the other counters, N, M, and K. Yeah, not everybody uses IJK. N, M, and K will commonly serve the same purpose. And if you're as good as me at your ABCs, you might think that N, M, K is a bit of an odd order, because in the alphabet, M comes before N. But N usually comes first when we're using them like this, just because N represents natural number. So it's like the best choice for just one number, but if we end up needing more, well, then we just use nearby letters. It's kind of funny. P, Q, and R, that's a trio that shows up a lot in number theory and also for logic. Those could be 3 statements, P, Q, and R. I kind of like this mention of the small values for infinitesimally small numbers that are way less than 1, but still greater than 0. Epsilon, delta, and eta. I'm not sure where eta is used for infinitesimals. Maybe I'm just forgetting, but you could tell me in the comments if you know. Then another trio that kind of doesn't belong, but certainly is famous, is pi, E, and Phi. They are, of course, the three most beloved irrational numbers. But let me know in the comments what your favorite mathematical trio is. I've got to say, mine is still my ultra-rare sealed Texas Instruments TI-108, my ultra-rare sealed Spanish version Texas Instruments TI-108, and my ultra-rare sealed Texas Instruments School Kit for Students TI-1106. And be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the cable. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue
Planet faded.
Psychosomatic habits, why you so